Great to be here and to talk about this really amazing work. Actually, I just love talking about this work because it's just been such a fun experience. And I guess a lot of you might have had some of this from Moritz, so I apologise if there's some overlap, but I'll do a kind of refresh of the main results from the DELPHI model, which is this continuous time multi-disease generative transformer model, which was published in Nature September last year, which is really good. So, and it's been a fantastic collaboration between us. So that's myself and you and Bernie and Moritz Gerstner.
And you have put DELPHI 2 up as the title.
DELPHI 2M. DELPHI 2M.
Yeah.
So that refers to the number of parameters in this regional. But then I will go on and tell you a little bit about extensions that we're currently working on. And I'd love to have some thoughts and ideas about how you might leverage these types of models for causality. So that's a difficult subject and an interesting area for innovation, I think. So, yes, I don't know why I've got this slide here, but this is me. I'm obviously, although I work at the EBI and I basically co-run the Bernie's research group. I've been there over 9 years now. Yeah, and so as I said, DELPHI 2M, it's been probably about 18 months from original conception to publication in Nature, so it's been a really kind of fantastic journey. And it was published in Nature in September last year, and it's really generated huge amounts of media coverage, which has been really fun and amazing, and we're still being asked for interviews from various different media outlets. But you know, one of the metrics was it had at least 900 media articles in over 80 different countries. So that's really, really cool. So you may well have seen this or be familiar with this type of architecture. This is the only kind of diagram that I've got in this talk. This tells you what DELPHI is. So it's a generative transformer model. Actually, it's a decoder only. So you know, that is not, and this is just showing you this kind of standard layout of how these transformers tend to set up with, you know, these causal attention masks and self-attention blocks and others. We made some key changes to the underlying architecture, some of which are listed here, but the key one really, one of the key ones is this age encoding system here. So rather than using positional encoding, which is now a standard transformer set up a position of text in sentences, we've changed that to be a continuous time age encoding, which allows the model to be optimized to predict not only what's likely to come next in the sequence of events, but also when, and that's really kind of key for healthcare modeling. So what's the data set that we're talking about? So of course we all know and love the UK Biobank, and that made a lot of sense for us to train our modeling. But we're very fortunate. We've been working with colleagues in Copenhagen for many years, Søren Brunek and others, which allowed us to have access to over close to 2 million Danish individuals from the Danish healthcare registries. And we kind of set this up in a very traditional kind of way. So we trained the data in the UK Biobank, splitting it for 80% training data sets, 20% horizontal validation. And then we also excluded a certain number of events based on time. So we could do longitudinal validation, which really was a really nice kind of proof of the model. And we're very fortunate to have this completely held out zero-shot test data set for this 2 million individuals in Denmark. So it's really nice data set to work with. Just this little schematic at the bottom just shows you a bit about, you know, what we're talking about. So we're not talking about any really extended data sets for the basic DELPHI model. We're just looking at healthcare events across time with some basic demographic information. So sex, smoking status, alcohol consumption, and BMI. That's all that was used within the original DELPHI model. And remarkably, so the model can predict all disease that it sees within that vocabulary. So all disease ICD-10 coded disease codes in the UK Biobank. It's about 1,200 or so diseases, individual diseases. And quite remarkably, we get very good predictive performance across the board for a large section of those basically 10 diseases. And you can see the performance here in looking at AUC values. And this, important to say, this is for the next event within a trajectory. Sometimes some diseases are actually quite simple to, or easier to predict than others. For example, death, which is shown in black, actually those two dots up at the top, is quite easy for the model to predict because you accumulate more and more health events as you age, and so as you're approaching death, the model has more information to base its predictions. But there are, basically across the board, we've got very, very high prediction for this type of model and able to model all disease all at the same time, and that continuous time. Also, if you look across the different classes of disease, there's no real biases. There's a bit of difference between different classes, but there's nothing that strikes you. And also there's no observable sex bias in aggregate across all diseases.
What's the time period over which you're predicting?
So this one is literally just the next event. So it's the next event within everybody's irrespective of time. But you can, and we do, look at large gaps within our AUC predictions. I'll show you that in a little bit. But it's, this is kind of potentially the simplest, but actually we find that the predictions maintain accurately for many years into the future, variably so between diseases. So we were really lucky to have this really fully zero-shot test data set in Denmark. And we essentially took a trained DELPHI model, which was trained in the UK Biobank, and only evaluated it in the Danish setting. So we didn't do any retraining or fine-tuning. And that's all summarized here in one slide. But basically, we're looking at the AUC values for those 1,200 or so diseases. And you'll appreciate that actually on the whole, we've got really good performance. And when you look at the direct comparison in the AUC values between those evaluated in the Danish cohort versus the UK Biobank, there's a remarkable correlation. And that is quite remarkable. So we've trained the model in a different healthcare system. We've taken it into a completely different country's healthcare system, and we still are able to maintain a decent level of predictive performance in a totally different country. So that was really, really nice to see. And I think one of the real proofs that our model learns some generalization is generalizable across different healthcare settings. Okay, so as you asked, we can look at different time gaps, and this is quite an extreme example where we're looking at a 10-year time gap and the delta AUC. So this is the drop in AUC performance for all of those diseases. You can see that there's, on the whole, everything decreases as one would expect, but actually it's not so bad. So it's kind of a mean of 0.05 decrease in AUC values, for example. And if you look at different time gaps here, so you can see from next event to 6 months, 1 year, etc., we have a very kind of consistent drop in performance as the time increases. On the whole, we obviously have different diseases which decrease or faster or slower than others, and that actually makes quite a lot of sense. So if you look at the curves in terms of how quickly the precision drops, more acute conditions such as cancer or common colds or anything else becomes much more harder to predict as you go further in time. Whereas other conditions like heart conditions or conditions which have some basis of previous information maintained for quite a long periods of time. Okay, so this I think is a really nice way to look at the model. As I mentioned, it's 1,200 diseases all mapped to the same internal space. But you can, because of the way that we've set it up with this age encoding system and the additional output head, we're able to interpret the probabilities that come out of the model directly as rates of disease on an individual basis. So every point in this plot is a person, and we're looking at the rate of 10 different highlighted diseases per year for that individual. And the lines are coloured for male and female differently, and they are the incidence rates across age for those different conditions from the UK Biobank. And what you can see is that on the whole, for these 10 diseases, the DELPHI-based rate estimates match quite closely with the incidence rates, which is nice. You can see some, but there is some spread, and that there are people who are thinks are at higher risk of disease than others, and that's essentially what we want to be able to do, is to pick apart at any given time who is at most risk of disease, and in this case we're representing that risk as a rate per year. Okay, and you can see some pieces of information that make sense. So, for example, chickenpox is much more frequent and probable early in life, whereas conditions like death or Alzheimer's are increasing much more later in life. Something like depression seems to be quite low in early years, increasing quite a bit towards late teenage years, and then remains relatively flat. And for example, the other one to highlight, I think, is heart condition, so acute myocardial infarction, where we have this increasing rate, kind of at that characteristic age point, 40 or so, or late 30s up to 40s, with the sex bias, no sex bias as well. So it's really nice to see that actually the model predictions kind of mirror what we know about health and also the incidence rates within the UK. One super cool thing about these types of models is they're generative. So you can not only produce point estimates of how likely somebody is to have one of those 1,200 diseases at any time into the future, but you can also simulate entire trajectories from some kind of starting point. And we did that, and this is what we're seeing here. So we've simulated trajectories, the same number as in the UK Biobank, simulated from birth, so they're only given sex information and some randomization of the lifestyle measurement. And we simulate entire trajectories, evaluate the estimated disease rates for all of these diseases between the ages of 70 and 75, so that's on the x-axis, versus the actual observed rate. So that correlation there for these simulated trajectories is remarkable. So the model really understands something about the rates of disease at different points in time, and can generate a meaningful, fully synthetic data set that is based from original trained model. You can then go on to train a new model using only synthetic data sets, and that's what we did. And you can see this marginal drop in performance for the overall AUC values for the real UK Biobank trained data set versus the simulated one. And that's quite useful. You know, that has quite a lot of different potential applications where one might not want to exploit real healthcare records, for example. Yeah, and we did quite a bit of work looking at kind of what the internal space of the DELPHI 2M model looks like. This is just one representation, so obviously a UMAP plot, 2D representation of really quite complicated space, coloured by the ICD-10 codes and the chapters, with the point size relative to the number of records within the training data set. And you can see a few things. On the whole, the different chapters tend to kind of be closer in space to themselves than other things, which makes some sense. And then if you look kind of down here, this black dot there, which is this ominous death token, which we do treat as a disease, is kind of close in space to some very acute conditions such as heart conditions and respiratory disease. So it's kind of quite nice, but as I said, it's just a 2D representation of what's really quite a complicated space. So another way to look at that is this SHAP analysis. So this is one way to, it's a method that's used to assess or to assign importance values for every predictor within an AI model to the predicted token. So it's a two-way thing. We're looking at the predicted token and the predictor token, and delivering some kind of an importance value that's estimated for that using kind of an optimized sampling technique to look at different contexts. All possible context actually is in here. And again, you can see this is for 5 years into these SHAP values are based for predicting the token 5 years into the future. And you can see that actually, as seen in the last plot, most of the disease classes or are more influential in the prediction of other diseases within the same class, which makes some sense. But there is some structure here. And for example, things like death is highly neoplasms or cancers are highly informative for death, of course, which sadly makes sense. But these are, it's worth saying, these are mean SHAP values across many different contexts. So they're kind of an aggregate measure and quite coarse grain in some sense. But there is some fine structure within even that coarse grain measure. Okay, so that's kind of a recap, I suppose. Many of you might have had Moritz talking to you about that before. One thing that we're really excited about, I mean, we just love this modelling approach, and the framework is extremely flexible, and that's cool because it opens up loads of possibilities. So we're thinking about various different extensions to the model. Some of which I've listed here. So, for example, adding drug information or prescription records, diagnostic tests, enhanced demographics. So we can think about people's locations, living locations, working conditions, environmental measurements, all types of different pieces of information that you can assign to an individual as a time point. Biomarkers, genetics, and lifetime exposures. So we're kind of working towards and making good progress in creating multimodal extensions for DELPHI. So DELPHI multimodal is kind of where it is. And we have a number of different projects going on within our group and some of our collaborators about how we best incorporate additional information inside the DELPHI style framework. And as I said, I'd love to have people's thoughts about causality in particular and how one might think about using randomization style approaches to look at causality within that space. We also have done some work which I think is super cool, is using these embedding spaces for GWAS style tests. But I'll just walk you through basically a bit of information about prescription record modeling and also genetics, so very kind of early start of including genetics within the model. So this is all about integrating G and E. So if you consider drugs as an environment, which I think is a fair enough point, and one way that we want to use these models once we've trained them is to look for these G to E interactions or pharmacogenetic interaction. Okay, so by definition, we need a G component and an E component. The G component is some representation of genetics, and the E component in this case is drugs. Yeah, drugs prescription. So we chose, for a number of reasons, to go with the HLA complex as the first way of thinking about genetics within the model. For a couple of reasons. They're quite a complex, as you will all know. It's a complex region of the genome. They come in multiple different states, and they tend to be inherited in long range, so they kind of inherit through family generations. But also they're very, very important for a number of different diseases, and they basically associate to everything within the GWAS. So we think that they would have potentially strong effects for predicting disease. Yes, and as any of you who've run GWASs before will be familiar with this chromosome 6 signal, which basically comes up in most GWASs. Okay, so how did we, there's a number of different ways that one might think about encoding this information. We, as a starting point, just went with the most simple, which is one hot encoding. So basically, look up table for every type of allele. And that, because we imputed the HLA alleles in the UK Biobank, that comes up to something like 200 different tokens. So that's additional 200 more tokens into the space. And you know, these genes encode for kind of this this protein, which presents in foreign invaders or molecules to the kind of immune system, and so they're very associate a lot with autoimmune diseases and other things. So we this slide gives you a sense of quite a lot of work that went in. So we trained a new, basically, which was pretty much exactly the same as the DELPHI 2M model, only that we have this one quite encoding for the HLA alleles, which are given to everybody at birth. And here we're looking at the delta AUC between the DELPHI 2M model and the new model, and I hope you can appreciate that actually we have quite a big shift, and we were quite happy or surprised actually to see this, that it makes quite a difference to the predictive performance across the board actually. But when you look at those which have the diseases which have the biggest impact from the HLA inclusion of HLA, they're very much enriched for infectious disease, autoimmune conditions, and cancer, which makes a lot of sense biologically speaking. And it's worth saying that we always present these AUC values as kind of the mean AUC across the various different time brackets. But actually we have age-resolved AUC measures. And here, for example, this is an autoimmune disease, psoriasis, which is known that or early psoriasis is very much driven by the HLA or genetics, whereas later in life it's driven by many other factors. Okay, and actually we see that in the models predictions as well. So it's quite neat. Yeah, and worth saying that we restricted this analysis to people with European ancestry only because we didn't want the HLA alleles to be like a proxy for ethnicity. Okay, so that's kind of a start with the G component. We're adding in lots more types of genetics, so the star alleles and other impactful variation. What we're not doing yet, I mean, might think about a way of doing it, but we're not trying to include the whole genome in this type of model. That would be kind of crazy. So I'll go a bit more into the E component, which in this case is drugs prescriptions, and this has quite a lot of really interesting work. Of course, we'd like to find G times E, but also just understanding multiple drugs across with multiple diseases across time is really interesting all of itself. So the prescription records in the UK Biobank come in a number of different coding systems, and we developed a framework, developed a framework called Prisoner, which basically maps all of those drug codes to ATC codes, which is a bit like ICD for drugs, right? So it gives you a hierarchical coding system. And we did that for cardiovascular drugs and nervous system drugs as a kind of first use case. We then trained a new model, which we call DELPHI CVNS for cardiovascular nervous system drugs, using kind of classical 80% training, 20% validation. And so here's just a very quick look at this kind of UMAP space. Again, we've got the dots coloured by the ICD-10 chapter, but also the different drugs. And what you can see is that actually not much in the UMAP space. Actually, the drugs kind of seem to be somewhat different. But central nervous system drugs seem to be closer in space to certain central nervous system diseases and also mental health conditions, which is kind of interesting. So I kind of explained what SHAP was before. Here's another, we're just going to have a look at the SHAP analysis, looking at specifically the impact of the drugs on predicting disease and vice versa. And what we really want to try to find is examples of, for example, adverse drug reactions. So are there drugs which are, when prescribed, are really increase the predictability or the likelihood of particular diseases, and in particular, unexpected diseases. So here is that heat map again. And again, you can't really see much. The next plot will be zoomed in here. But if you look at the drugs which are showing in purple and red, they are essentially predictive of each other. So once you get one drug prescription, you're more likely to get the same another prescription within the same class. But actually, even though you can't see particularly here, they are adding some predictive information to the expected disease class. So if you zoom in here, now we're looking at central nervous system drugs. They're predictive of each other, but they're also very predictive of mental health conditions and central nervous conditions, which are essentially what they're being prescribed for, and to a lesser extent, the cardiovascular drugs. But there's also some fine structure, and I should say this is these mean SHAP values across many, many different contexts. So it's quite a coarse measure. And also worth realizing that as you start to add more and more of these tokens and want to look at combinations, those combinations start to become very, very rare, very, very quickly. So, or at least the context of those combinations. So anyway, but there's some interesting things that we can observe already. Here is one somewhat useful way to look at this. So here we're looking at drug disease pairs, okay, and we're looking at the mean predictive SHAP value on the x-axis versus the variance in that SHAP value across different contexts. So essentially, what you really would like for a drug disease pair where you're adding a lot of predictive performance to the model for the prediction of that disease, you'd like to see the dots kind of down here, right? And then if you were looking for something that is potentially protective, you might be looking for something around here. So it's kind of a two-way thing. But what you can see here is this is looking at cardiovascular drugs versus circulatory diseases, mental health disorders, and nervous system disorders. And there is a shift, as one would expect, to circulatory disease. Actually, one important point to know or to just mention, is probably quite obvious, is actually the time point when prescriptions happen. And the reason for prescriptions very often follows the disease. So you might have had the disease, go to the doctor, then you're prescribed the drug. So the fact that it's not adding too much in the kind of standard MOS transformer training regime is maybe not so surprising, with some exceptions. And so here, when we're looking at central nervous system drugs, which are very often used to treat mental health conditions and central nervous disease, here we have a much stronger effect, which makes much more sense. So, you know, maybe prescribe that for as a kind of treatment. But there are also some interesting other observations. Yeah, and that's just really a basic view of our kind of first work of trying to integrate drugs into this type of model. But there's lots of additional research questions that we can start to answer. Yes, and I mean, just to show you some examples of what these things are. So that one there, this ketamine drug with schizophrenia, that's it's a frontline treatment for schizophrenia, so it makes quite a lot of sense. Whereas we've got some other interesting conditions where you've got a single drug which seems to be highly predictive of multiple things. And I think this one in particular is like a pain relief style drug that we use for many different indications. But there's a lot to pick apart here, but we still kind of want to get the the way in which we encode the drugs improves a little bit before we dig into more detail. And of course, what about other diseases? So this is kind of what I was getting at is, of course, you can look at all drug pairs, all disease pairs, and what you're really looking for is unexpected. One interesting thing is unexpected diseases here, which could be adverse drug reactions, and also protective functions of drugs for potentially protecting against disease. So that's kind of it, really. I hope that was interesting, very useful very happy and keen to have critique, questions, discussion. You know, we went through quite a lengthy review process for the paper, I should say, and we had, you know, we really did do a lot of work to address or to satisfy the reviewers' comments, but also just for our own sanity. But you know, we think there's real value in applying this type of model, both for research, but also for essentially understanding health across the whole population and across multiple population. So we're working actively on many different extensions to the model and additional data sets. So thanks very much. So that I'll just
So questions?
Potentially basic question. Can you tell us more about the time encoding? How does that work in a kind of that context?
Yeah, well, so I mean, it's the encoding itself is quite straightforward. So it's just based on sine and cosine encoding of the time domain. We have a additional output head, which is basically an exponential waiting time model. And the choice for that was deliberate because it kind of means that the time domain can remain relatively it can remain relatively calibrated across relatively large space periods of time. One thing that we had to do to make the model work, actually, with this, it was add something that we initially called healthy tokens, right? But then we decided to turn them into no event, or name them no event tokens, because it doesn't really mean that anybody's healthy. But we have to have a kind of hook to calibrate the time they make, and we spent quite a lot of time thinking about that. But actually, the simplest way that we went with for the DELPHI 2M paper is just a random or a fixed rate of inserting those kind of no event tokens, which helps the model to understand the time a bit better. Yeah.
So I'm really interested by the way you're doing predictions between, are you saying like, this is the likely next event and how likely it is? Are you saying like over 5 years, these are the events we think might happen? These are the likely sequences, you know, compared to traditional risk scores. What is it that, what is the form your predictions tend to take?
Yeah, so it would be, so if we were looking at kind of predicting an event within the next 5 years, then it would be masking information beforehand. So that's how it's done practically. When we've started to do quite a lot of work at generating full trajectories, that's tricky, as you might expect. So it's not likely that you're going to get exactly the same trajectory as what was actually observed. But it's quite interesting actually, because there are some, with some diseases which actually that likelihood of it occurring within a specific context is really not well calibrated, or do you have a lot of different variability in that in that probability across people. But then some which are much more reliable. So actually that kind of building up of that sequence, there's quite a lot of tricks that one could potentially do to make it more reliable. But we really only just started to look at had it, to be honest.
What are you, there's been a lot of discussion about whether the outputs of these models would be identifying. I mean, it always seems an extraordinary notion that you could reverse the processes, but certainly there's been discussion about using in a sort of trusted research environment case, the UK linked data that become available post-COVID.
Yeah.
But then only outputting the probabilities. But some people, Jonathan said, haven't been involved in discussions with some people think that these outputs will be identified. And don't want that to happen. You presumably been in similar discussion.
It's quite annoying. I mean, I think so I find it very difficult to imagine a world where the predictions themselves could be identifiable. You would always have to know something anyway. I think you would have to be, asking the model something. Maybe if you knew a little bit about somebody, you might be able to get some information. But it seems really rather over the top, although I understand that there's concern and we have these discussions with the UK Buyback and others about sharing the model weights, for example.
Yeah,
and
well, that's what we're discussing.
And at the moment
it's effectively constraining not being able to do that.
No, I know.
And it reduces usefulness.
Yeah, exactly. So we have deposited the weights back in the UK Buyback. They will make them available. We did that deliberately because you don't want to get into this, but I think it's an active area where potentially people will start to write methods that prove that the models aren't discoverable, aren't identifiable. I think the other concern, which is also justified, is like being able to replicate a resource so well that you kind of don't need the resource anymore for some application.
Yeah.
But yeah.
Good.
Congratulations. Just really, I don't know how you thought of it. It's just amazing. But so one of the things that I tried to understand is, so you use this like sort of LLM style model, and the reason that, as I understand it, the reason that LLMs do so well is because of this thing called self-awareness. And in like statistical terms, like what that means is like it's putting in this really high order interaction term, right? Like, and so the idea is that the tokens are totally nonlinear. Like what happens next is highly dependent on context. And I just wondered, like, I think it's, I don't want to play down what you've done, but I think like the AEC is like, it's really good. It's probably better than most of the models, but it's not like drastically better than lots of other models. And I just wondered if you had any like insight as to like what the model is leveraging to get better, and if it tells you something about the non-linearity of the human life forms, like do you think it is highly nonlinear?
Well, I think in some cases, yes. I mean, so I think there's a few things in there. One thing is the biases within the model, and actually we did a lot of we did a really extensive look at potential biases in the UK Buyback in this model. I think we did a really good job of it. And there are some which exist, which the model actually uses to improve its prediction. Right? So, for example, there is the healthcare records come from 4 primary sources. So hospital records, GP records, self-reporting, and death registries, I think. That information is not available to the model during training, but it learns that there's some structure in the different token sets. So if there's one disease which is very often seen in hospital, for example, if that occurs, the model tends to upweight all of those hospital-only codes. So there's some intricacies which it does. But I think the primary thing is that it's capable to look at all of those diseases all at the same time and model complex interactions which wouldn't really be able to do in a traditional modeling framework. We actually had to compare against every other's kind of model that one might be able to think of during the review process. And actually really encouragingly, on the whole, the model is as good, if not better than currently clinically implemented models, with the exception of one which was based on a biomarker.
There's one.
Yeah, but
Is it, have you tried combining? Just, I mean, you could obviously just combine and see what it adds over Vallingham score or whatever's currently used. Have you tried that?
We haven't done specifically with the scores, but what we did do is we looked at combining the biomarker data in the UK Biobank and the PRS, the polygenic risk scores, and that made a slight marginal difference, and in the kind of diseases that one might think. So the inclusion of biomarkers, for example, helped quite a bit with metabolic disorders, which made quite a bit of sense. But we didn't, in the paper, we didn't do that formally within the model, but we're now working on representing that biomarker data and genetics more formally inside the model.
I can't work out whether Jonathan, I thought you were scratching your ear. I was asking a question.
Because of the famous ability to multitask. It's absolutely fascinating. Could you just, related to what you just said, could you please just say a bit more about what data from UK Biobank went in here?
Yeah.
Yeah, because it's slightly unclear to me how the vast range or.
It's a really good question. So we deliberately went for the first occurrences data only. So this is healthcare data that has been kind of massaged and curated by the UK Biobank, and it essentially uses ICD-10 codes, but only the first occurrence of every code within any person's life. So it's that code and the date at which it was. So that's the majority of the data. The other ones were sex, smoking status, alcohol consumption, and BMI, categorized actually. So those we didn't try to model them in a continuous way. They were just high, medium, or low.
And repeated over time.
And repeated over. You mean the lifestyle measures repeated over time? No, they were. So there's a technicality here. So they are measured once at recruitment. At first, we inputted them into the model at the age of recruitment of the individual, but that then led to some kind of recruitment age bias, right? It's kind of weird. So we had to end up kind of randomly. That was the kind of slightly hacky thing that we did, is for practical reasons, we just kind of randomized a little bit the time at which we put those lifestyle events. But ultimately, you basically want to have that information available at multiple points across somebody's eye. The other thing that we're looking at is, of course, this was based on first occurrences data. So there's only ever one occurrence of each disease in one individual, but real healthcare records can have repeated diagnoses, and it makes sense to actually try to, well, at least evaluate what difference that makes to this type of.
Presumably, given that all the biobank measures of, for example, BMI were made in middle age, you had to avoid using middle-aged BMI to predict childhood.
Yes, exactly, and smoking, and also so that type of thing. So there are some kind of weird gotchas actually in these results.
But no, because you have reported body size pre-pubertally biobank.
So for which are they used?
Well, I know you'll be using the adult one.
Yeah.
But I mean, you can use those things as
No, but I'm
a sanity check. You can use them
Also,
sanity checks. Yeah. I mean, for MR, the sanity checks work because you do MR of child with BMI onto childhood vitamin D, and adult with BMI onto adult with vitamin D, and you put them into a model together. Child with BMI is the influence in child with vitamin D, and the adult with BMI is influence in adult with vitamin D. So it works beautifully. So,
Yeah, two questions. There's time, and that's one quick one. So when you're doing the genetics, are you using external association information, or are you literally letting the model re-find that genetic phenotype association?
Yeah, well, so what I showed here was just the HLA, so that's kind of using genetics as a predictor for disease. So different. But one thing that we are working on, and I think is really cool, is trying to run GWAS style tests from the embedding space itself. And what's cool there is that you can actually look at time resolved GWAS signals, and you can find embedding vectors which are are basically associating to specific genetic signals. And from what we've seen so far, that makes a lot of sense in terms of those embeddings which are impactful for predicting particular disease, are also predictive of the genetics underlying those diseases. But I think one thing to be really careful about, which I kind of said, is the causality of these. Like, they have such a large space, so many parameters, they can take shortcuts in lots and lots of different ways. So if you're saying, if you want to do causality, then really genetics would be one way, I think, to kind of either force the model to be like a causal model. I mean, but I haven't really thought of how practically that would work.
You can sort of definitely force them, and then you can call it that.
Yeah, well,
Actually, yes.
And then the other question I have about the drug disease stuff that you did, and when you showed the plot, you were saying that the things down the bottom of that plot were most interesting. But I just aren't the things that are higher up on that plot potentially where there might be precision medicine opportunities?
Yeah, certainly. I mean, I think that it's kind of, there's a lot to dig apart there from showing those kind of simple plots. But you're right. When something is really variable across different contexts, that's super interesting. But the problem is that we end up getting to low numbers very quickly. So you really need the whole population really to get. But that's definitely interesting to look at.
Oh,
Yeah, I have another question sort of about the genetic information. Have you thought much about how you're going to scale up from HLA? We saw an interesting talk here a couple weeks ago about people trying to use exome sequencing data, treating that genetic data like it's an image.
Okay,
Interesting way of doing the encoding. But curious.
Yeah, I mean, we're definitely thinking about it, and that type of approach of having a encoding system that could be an encoding of the genetics in some sense. Maybe you just take all known genetic associations and create an embedding of that. Then that goes into our kind of multimodal extensions, where actually you can just use that embedding space and map it directly into the decoding space at some time, maybe at birth. But yeah, so there's definitely lots of scope there to do interesting things. I think adding all variants would just be unfeasible for a number of different reasons. So you need some kind of embedding, some kind of encoding upfront.
there's a question online. Online says the authors argue lots of disease risk is due to random stochastic processes. That's true. Prediction difficult. How does this idea fit with your GPT results?
So George is wrong. It's perfect.
No, it's actually really fascinating. So there's definitely a lot of stochasticity in the model predictions. And actually, if you look at this UMAP, I'd say explain my take on this. So that UMAP, right? Basically what happens, and it's worth knowing, as somebody ages, they move around somewhere in this space. And we generated some videos actually of different people journey around this space. And it's really like a pinball. So, you get pulled to one place versus the other. And as soon as you get one other thing, you might jump somewhere else. So it really, there is a lot of stuff.
You say it's like Brownian motion. If it looks like Brownian motion, then it's stuck.
Yeah. Yeah, it's literally like that. Yeah, but of course, I mean,
It'd be good to get the two videos together. The video of Brownian motion.
yeah,
I'll
so-
pay for that.
but so there's a lot of stochasticity, but actually the ability of the model to separate people at particular times for high risk is really quite remarkable.
Thanks, Tom. Are there any more questions online? No idea.
It's just showing us reason.
Oh, that's a good. Futuristic. Jonathan. Oh, sorry. MC.
Yeah, I'm just wondering, have you ever tried to run DELPHI on a non-European section?
Not yet, but it's on the list.
Oh, is it already? Really interesting to see.
Yeah, it would be. Yeah, certainly, definitely. I mean, I think it's valid to say that the Danish population and the UK population are probably quite similar from a healthcare point of view. So it'd be interesting to see, is there a population where we see a really big difference? What we spent quite a bit of time trying to look for surprises. If there was something that was really predicted in the UK and not in Denmark, for example, it could be that it's a different way that disease is coded, but also more interestingly, it could be that one healthcare system is doing a better job than the other, kind of thing. But we didn't really find anything that made that much sense.
It's like such a different style of healthcare that you were going to transfer to. You probably wouldn't want to just do a zero shot transfer, right? Like,
I think you would always want to retrain.
Yeah,
I think so. I mean,
Yeah.
optimally. Yeah.
Got one last question, Jonathan. The last question.
Can I just return then to this disclosivity thing, which clearly irritates me? The example that Benny Goldacre uses is that in the electronic health records, you could perfectly easily identify Tony Blair.
Right.
Because all you'd have to, it's well known that on 2 particular months, he had cardioversions for atrial fibrillation.
Mhm.
So that, plenty of there's enough publicly available information about people, or if you were stalking somebody, you might know enough about them to be able to go and uniquely identify them and then probably find out confidential stuff.
From the actual data, yeah, absolutely.
But you would
But
still
here, you've
Yeah.
got a model with, I don't understand it, but several million parameters or tokens or whatever you want to call them. Does that concern simply not applying the model, or are there circumstances in which, with access to all the model parameters, you could get back to individuals? That's the concern.
Yeah, I get it, and I think I would say super unlikely, but not impossible, right? And I think that's how everybody's kind of framing it right now. But there needs to be some work to really assess that. I just can't imagine a world where you would be able to regenerate somebody's history perfectly from the model weights system. And it just doesn't seem feasible to me. But not having no information about them at all. But I think we've kind of gone through this process with genetics quite a lot. It's identifiable information within the genetics world, and that's quite a well-trodden path. So I think there's quite a lot of analogy useful when we're having these discussions with the data.
But generally,
Code.
genetics was consented. And the point here is that the big power is unconsented population scale electronic health records. But I mean, I just think that I was interested by your information that the interesting point is, well, that's the concern. If you want to understand the concern, people like you understand what these are things are doing, as opposed to me who understands nothing about these about this work. Should to find specific reasons to say it won't be possible. to do.
Yeah, exactly. And I think that's what needs to happen. And there are people working on methods to show that. I mean, one way that might be easier. So, I mean, I get the concern, and I think it's right to have these safeguards in place. Bad things can happen.
Yeah.
But one thing that you could potentially do is generate this kind of synthetic data set.
Yeah.
Prove that there's nothing in there that is same as the original data set, and then that trained model seemed a much easier kind of justification. I mean, I think the fact that the model is trained off real data immediately makes that there is a connection there.